So I think we'll wait one more minute and then we'll get rolling. Hi, welcome. Yeah, grab a sheet and okay, Sarah. You want to start?
Yep. So I and welcome to today's ITC discussion, and our discussion today will be head by Morgan MacLeod and focus on the new class of fast blue optical transients and the development of new theory to describe and explain these objects. And so Morgan will give a brief introduction, and then the floor will be open for discussion, to which I encourage you all to contribute. And our aim here is to split the floor time evenly between all the contributors. So off you go.
Thanks so much, Sarah, and thanks everyone. So let me tell you a little bit about my plan for today. So we're going to talk about this class of transients that are extremely interesting. They're relatively rare. They're also relatively newly discovered. And if you don't have a sheet, find one. Evan. And then, so what I want to do is I want to go through a few of these pictures and summarize some of the main properties of this class of objects by looking at one particular example, the most famous example. And then I want to pause and we can talk about those properties and try to summarize them together. And then I want to step back and we'll look a little bit about some of the kind of like basic scalings of how light comes out of an explosion, like a supernova, something like that. And we'll look at how that relates to ejection energy, ejection mass, that sort of thing. And then I'm hoping that we can kind of group up with the people around us and you can come up with your theories. And then we will, and some of you have a head start, but so maybe that group in the corner will have an advantage. But and then at the end, I want to sort of regroup and summarize what we came up with, and I can tell you some of the ideas that are out there in the literature, and we can look at how our thoughts compare to those. So that's kind of the basic plan for today. Okay, and then I guess the other thing to mention is that in the context of these discussions, I think some of the discussions that we'll hear, like last week we heard about the sort of amazing mapping of the Milky Way that Alyssa's group is doing. And that represents something where there's the years of expertise that are built in that area. This is sort of the other half of these discussions. The idea was that it would be kind of topics that one of us would be assigned to dig into. And so this isn't an area that I've published extensively and in the same way that Alyssa has in that area, but it's something that I'm learning about, so we're all learning together here. Okay, so the first thing to point out is that these transients, as you may know, a lot of transients get assigned by their year, and then a series of letters that are automatically assigned. I've been told that because those letters are automatically assigned, there's work that you have to do to make sure that it isn't a bad word, and the way that they do that is by checking against a list of like 10,000 words that it shouldn't be. And so that's kind of delightful if you think about that. But this one came out to be 18, what?
What happens if there's a match?
Well, then like you pick a new random letter combination.
So you don't hide.
That's something to avoid. But this one came out named 2018 COW cow, and along with the fact that it was sort of mysterious in its origin and different in its properties from other supernovae, that sort of started a lot of fun. And the events in this class after that have all been named after animals. Whatever's closest in the like random letter generation to what, so the most recent one is like 2023 FNC or something like that, and so they called it the finch. But there's also been the koala, the camel, the Tasmanian devil. And so these, are a zoo of transients. And let's talk about what makes them interesting. And I think I'd like to look first at the...
Morgan, can I, sorry,
Yes.
just interject, but I think
Please.
doing it earlier on would be useful. I think,
Right.
with these things, it's always important to have the kind of longer term, I think, historical perspective of where these things
Yeah.
kind of sit. And I would say that, well before any of these individual events, which have really amazing data sets, partially because they're relatively nearby, really the class as a whole was defined, earlier in 2014 in a paper that Maria Drought wrote as part of her PhD thesis. And that paper was based on the Pan-STARRS medium deep survey and doing a systematic search for fairly rapid transients with shorter duration than normal supernovae.
Yes.
And it uncovered 10 events, so a bigger sample than this handful
Yes.
here. That it wasn't clear if they were all coming from a common origin, if they all had the same physics, but they were observationally defined in a way that, I think created this class. Now, I can't remember exactly what we called them. It was something like rapid transients.
They were
fast
like
transients.
rapidly evolving,
Yeah, rapidly evolving.
luminous
So the names have
transients.
been
Yes.
kind of changing, but 2018 cow, when it was discovered, is kind of, I think it was within the context of searches for these kind of transients. It was already motivated by the fact that we knew that there was a sample of events out there
Yeah.
with a fairly high volumetric rate, but that are hard to find because of their short time scales.
And
So I think just placing it in a bit of a
no, that's
context.
fantastic. And I think if we look first, and I'm hoping you'll keep chiming in, if we look first at the upper right sort of panel C, what we're looking at here is kind of the time scale of a transient compared to how bright it is. And all of the black points, I believe, are from Maria Drout's 2014 paper. And basically in Pan-STARRS, because of the cadence, right, I think that you catch a fast evolving transient like this in a few frames, right? My understanding from that work is that you have a sense that these are appearing and disappearing really quickly. And at some point in their light curve, they ended up with this name fast blue optical transients because they're quite hot and quite blue. But Maria identified most of those kind of in hindsight, right? So there was no opportunity to sort of follow up on them or apparatus to move that quickly. At
So
that
we just
point.
had light curves, no spectra.
I think some of them had spectra, not all. It's also the nature of the medium deep survey of Pan-STARRS is very different from current surveys like ZTF. in the sense that it's a pencil beam deep survey. So it's a small area, but very deep with fairly high cadence. So like the dark energy survey, supernova search, and so on. So those are good at finding distant objects that are dim, as opposed to things like ZTF, which are wide field and shallow, which are good at finding nearby things, which are apparently brighter. So I think that's also the trade-off, is that some of these were harder to characterize because they were dimmer and at larger distances. But I think they really motivated the searches in the ZTF data and other data streams to specifically look for things that evolve rapidly with some very basic definition, X number of magnitudes and Y number of days.
And as I understand it, didn't that work also sort of set into play some of the efforts to increase the cadence in a subset of the ZTF sort of fields?
I think these dirty fireballs are really what drove that. You probably will talk about this, like what possibly could power something so short,
yes.
right?
Okay.
Yeah, and relativistic events are one possibility.
Yes.
And, so the PIs at CTF have been very interested in this like dirty fireball problem, some failed sort of jet
Yes,
for a long
I see.
time. Yeah.
I
So
see.
I think that was the motivation originally.
Interesting. So if we look at the light curve on the left, this is kind of like then the first event where we have tons of photometry, tons of spectra, and multi-wavelength data. Is that kind of a fair description? Yeah, so if we look at this photometry, there's a ton of bands here, and I think the thing that I take from this, and what I'm hoping that you'll notice, is that it drops really fast. Okay, so we don't see it on the rise. Some of these, others of these events, we do see them on the rise, but it falls away really quickly, and the B minus B color in that upper panel is about 0, so that's like the color index of Vega, and it doesn't change much. And then if we look on the lower right-hand side, this is kind of compared to all the other types of supernovae out there. And what you can see is that at peak, this thing is pretty bright, so it's as bright as like a 1A or a 2N, but it falls away so steeply, and there's this dashed line for nickel 56 decay. So nickel decaying, radioactively decaying, has a half-life of I think 7.5 days, and so that if that is the energy source of the luminosity we're seeing, it sets kind of a slope in this magnitude versus time diagram. And I think what you can see right away, and we'll come back to this, is that this thing is falling away much steeper than that slope. And that told people right away that maybe nickel isn't the power source that is driving this luminosity that we're seeing. Okay, if we look at this spectral series, what you're seeing is the brightness of the source decreasing over time from the top line at 2.2 days down to the bottom line at 53 days. So the text there is the time in days. And it's a combination of the sort of photometry, the SED at sort of in mostly the UV and IR, and then the optical spectra. And I think the interesting things to note is that at 2 days, this is basically just a featureless spectrum. But then at sort of 3 days, 4 days, 5 days, what you see is this really broad bump almost across, like from 5,000-ish angstroms. And that sort of broad, almost like wave-like feature is an extremely broad line. And if you ask how broad is it, it's like delta lambda over lambda is about 0.1. And that tells you that the Doppler shift, the Doppler broadening of that line is about 0.1 of the speed of light. So the characteristic Doppler broadening. As you go on, the features in the spectrum get narrower. And something else that you see that's not labeled here is like hydrogen lines, helium lines, metal lines all appear. And the characteristic width of those is something like 0.01 C. So a transition from, a few by 10 to the 4 kilometers per second to a few by 10 to the 3, a few thousand kilometers per second. Okay, let's go to the next page at the top. And I'm showing you all pictures here from a couple papers on this source, one by Rafael and Margutti and another by Dan Pertley. But there's a bunch of co-authors each of those because, and there's sort of similar plots in other places. Okay, so one thing we can do from those broadband detections is put together the bolometric luminosity. And so this light curve on the left has a few components. It has so the 0.3 to 10 keV and the 20 to 200 keV markers are the X-ray and then the hard X-ray detections of this source. So this is really like a multi-wavelength transient. And then the black points that are labeled LUVOIR are ultraviolet, optical, and infrared light coming out of the source. And then the yellow points, which are labeled L engine, for our purposes for the moment, are essentially just the total, the sum of those lines. And the idea is that there's some intrinsic luminosity that's coming out, and it's the sum of the parts in the different portions of the spectrum, if that makes sense. Okay, so if you have a component of thermal emission, and you know the luminosity, and you estimate the temperature based on the colors, that's this upper right-hand panel, then you can use L is 4 pi r squared sigma t to the fourth and calculate a radius from that temperature and luminosity. And that's what's here. So if we look at this temperature and radius evolution, I think the things to notice are the temperature looks like it's going up and down, but we're on a scale of 1 to 3 times 10 to the 4 Kelvin. So really it's kind of mostly staying at a few tens of thousands of Kelvin, the photosphere of this object. But what is happening is its size is changing a lot. So the emitting area of this object is staying a similar temperature while it's getting much, much smaller over time. And at face value, it's kind of interesting to examine that. So when a star blows up, at least the thing that I think of at first is, wouldn't the photosphere follow that expanding material? And so what we don't see here, for example, is a photosphere that's moving out at 0.1 the speed of light, which was the width of those lines early on. We see a photosphere that's actually hovering at a similar location and then eventually contracting even as material is flowing out past it. So the photosphere isn't following the sort of expanding ejecta, it's sitting in one place as material is moving. Okay. So I thought now would be a good time to actually pause and both have space for sort of questions about these properties, and then I wanted to list together on the board what kind of the key features we think are of these sources.
Morgan, I don't know if you're planning to talk about this, but one of the other interesting features of this transient is its radio and millimeter emission, which track the interaction of the fast-moving material with the pre-existing circumstellar.
I was going to share a little bit, but now would be a great time. So do you want to tell some of the main properties, or do you want me to talk a tiny bit about it?
I kept my mouth shut. Well, I would say generically speaking, when we see quite a wide range of transients emitting in radio and millimeter, and it's generally a very different process from what produces the optical emission. So it's synchrotron emission from the collision between usually the fastest moving component of ejected material with some surrounding pre-existing medium. So it could be, in the case of a supernova, a gamma ray burst, a tidal disruption event, it doesn't matter.
Yeah.
It's a very common type of physics.
And if we look at this same plot, if we can pause for just a second, when you can't see it in this plot, but when you decompose the SED, what you see is the ultraviolet optical IR, the UVOIR, is essentially a thermal portion of the SED, and then the X-ray and also the radio, which isn't plotted here, are non-thermal contributions. Yeah.
So I think in this particular case, the millimeter emission was particularly luminous, and it gave an indication of a very dense medium in the immediate vicinity of the progenitor system, whatever massive star it is. But that's another independent clue about the overall structure of the system
Yeah.
prior to the explosion.
Yeah.
As well as the velocity. So the velocity of the ejected material can be inferred from the properties of the evolution of the radial millimeter emission. So that's an independent kind of evidence for very high velocity. No, I think it was up to about a third the speed of light or so.
That's right.
For some of the ejected.
That's right. For the earliest sections, right? And then it evolves to lower velocity and lower densities.
Also, just to add on this one, like I think like one of the what is missing from this one, there was one discovered in 2016 data from CSS something.
Yes.
I don't remember, and that has like very high velocity of about half of the speed.
0.5 C, right? In that
So that
source.
was something like very unusual.
Yeah.
One of these.
Yeah. And Diane Kupchins is the first author of that paper.
One thing I would add, which I think is an important clue here, is that when we look at different types of supernovae, so the explosion debris doesn't all travel at a single velocity. There's some depth and velocity profile that is imprinted as the shock wave propagates through the star and interacts with the density profile of the star. So we see that more compact stellar progenitors, once they're stripped of hydrogen, produce higher velocity ejecta from their very tenuous envelopes. And this falls in that category, so it would, I think, provide some evidence that the progenitor system here was quite strict.
So this feature though, that's broad at early times, was that identified? Is it H alpha? Because then it's not strict. It's confusing me a little bit, because I don't remember the story.
Yeah, I don't think it's H alpha.
Is it
So to my understanding, or to my reading, that feature wasn't actually identified.
Okay, great.
At least in the, that was 2019.
But we're confident that it's an efficient feature, that it's just very Doppler broadened.
Yeah. And I mean, basically, if you think about if its spread is 10%, there's a million lines in that region.
Yeah.
Could be. So it's very hard to say that it's for sure, line X. Let's talk about some of the features. Yeah, okay. So, Sarah.
Yeah, so I'm just slightly confused here. Yeah, this is, yeah, but like an object, still that's ejecting things. Is there a reason it shrinks over time? Am I misunderstanding the
Yeah, so
of this spread?
what I think is happening is, in a source like this, is that the material itself is going out, and as it goes out, its density goes down as a function of time, and so eventually we start seeing deeper and deeper and deeper inside of it in terms of like mass coordinate, you can imagine. So
So like you're saying the edge is not detected, and so it expands.
Yeah, so essentially the edge becomes transparent.
Shrinks.
That's right, and what you see in a normal supernova is like maybe nebular emission from those transparent parts, and then some photosphere somewhere in that flow,
I see.
and then there's some portions that are still obscured. And yes, so what are some other properties? Yes, Vinny.
Is this velocity that you refer to, is this independent from this measurement of radius, or the radius somehow, the way how the radius is derived somehow conversed?
It is independent of the radius because it's coming from a L is 4 pi r squared.
So is it fair to think that this velocity that you infer, it's within this radius that we see
There's
for, yeah.
there's like two, maybe velocities, several, but the one, so where the lines are forming, they will take on the velocity at that kind of layer of ejecta, and so at this point the photosphere is in a very rapidly moving case, and so that's what we're talking about with this 0.1c. But then there's this other measurement that we're talking about where I can track that photosphere over time and then do like a DRDT, and that's telling you not about a physical moving piece of the ejecta, but it might be the fact that it's receding or something, and just tracking the photosphere.
So it's like an expansion of the bubble, or
There's an
it becomes
expansion
a-
of the ejecta, but exactly as Morgan said, eventually that becomes optically thin, and we're
Right.
just tracing the optically thick component with this like
I see.
Boltzmann equation.
Yeah.
I mean, I think the important thing to remember is that there is no single velocity. There's some velocity profile. As your photosphere recedes through the ejecta, it samples inner and inner parts which have lower and lower velocities. So you see high velocity at early time, and you see lower velocities at late time, not because there is deceleration, but because you're looking at a different mass score.
Yeah. And even if they all started at exactly the same moment, at the same location, which isn't exactly true because it's a star and it's blurred out, but like the fastest ones would get out ahead, right? And so sometimes we talk about like this material being in homologous expansion, but it's sort of like the universe where like, you know, the further away you look, the like more the velocity difference between 2 points.
I just want to understand, I mean, I get that picture.
Yes.
When I think about a photosphere and supernovae, my intuition is that this makes sense because most of the energy was actually emitted in the core, and you have this ejecta, and the photons are trying to get out past that ejecta, and that's why we talk about a photosphere. As opposed to a relativistic jet where the energy is actually mostly in the outflow, and then I would think that it would be more about like the energy conversion as the material is hitting things. It's not
Yeah.
So then I don't have a concept of a photosphere as much. Is that
Can we come back to that in just a moment?
Yeah.
But I mean, the photosphere in either that kind of relates to both where the energy source is
Right.
and how much of it is getting out.
right?
But the photosphere in either case is just a function of the opacity and the size,
The
right?
photosphere is, but it's a question of whether, I mean, in certain jet configurations, it would be, the thing is always effectively kind of optically thin. It's just a question of where you're actually,
Yeah.
where the energy is being converted to
Yeah.
photons that are getting.
Okay.
And
Understood.
also, maybe just to point out to this, if it's helpful, is like, this is also why, like, Morgan has made a distinction of non-thermal versus thermalized emission, because in the thermalized set, we are always gonna have this photosphere until it
Yeah,
reaches
that's
nebular
fair.
phase.
Yeah.
Oh, interesting point. Yep.
Yeah, I mean,
Okay.
the fast outflow or a jet is the part that produces the non-thermal,
Yeah,
synchrotron radiation, and there you have
and then we
synchrotron
don't
self-absorption and
use
things
yeah.
like that, but it's a different.
And the synchrotron self-absorption is what helps you estimate the density of the CSM.
Yeah.
If we can, let's come back to that in just a second. Other properties are, one thing that I notice is like slower later. So there's like velocities of the order of 1% of the speed of light in these line widths at later times. What else did people notice? So Ito mentioned like non-thermal emission. There might be some circumstellar medium, the CSM, some emission mechanism that isn't just the sort of like thermal emission from expanding material. What else?
I guess it's more implied than visible on the plots here, but it's very fast rise time, right?
Yes!
Do we see the rise time in some of these?
Yes. We do in some of them. Some of the nicest plots are about this one, right?
I also saw like a variant of this C plot where people also measure like very fast rise and very fast decay. So they measured this D half of like rise and decay together and then compared it with the other Transients. So it was also one of the standout in that term that it's very rise and decay very fast in the very.
So not just, yeah, because some of these light curves are asymmetric, right? Where you might have a fast rise and a slower decay. This has like fast decay also. Is that a good summary of what you're pointing out? What about the color? I'm not asking something deep here.
Constant-ish?
Starts with a blue. Yeah, blue and constant. Thanks, Evan.
But is it actually, I mean, so these temperatures measured, and is that a statement that actually, as you get into the UV, it actually does turn over?
That's a statement, yes,
It's not-
about
it's
the
not just
thermal component of the
It's not a
emission.
power law.
Yeah, so basically the fits, if you look at them, are like a black body plus a power law. And the amount in those two components varies over time, and the statement about the temperature is just of the thermal component. Yeah. Anything else?
Is it clear from this plot or what you said?
The temperature evolution is clear either from the B minus B color not changing much in the very first plot, or from the inferred temperature fit in the second plot, on the first top plot on the second page. Yeah, Ashley.
I was gonna add something that I generally don't know. The cow, at least, is in this beautiful spiral and pretty well embedded within it. Are all of this zoo within star-forming galaxies?
Some of them seem to have relatively large offsets from their hosts, as I understand it, but more of them are associated with sort of recent star formation. Yes. Ito, is that correct to your understanding?
I think it is. I think the other thing is a strong X-ray emission. It's not very clear.
And in terms of the X-ray luminosity, like what is the X-ray luminosity of a normal supernova? You know, for if we're looking at say 10 to the 43 ergs per second coming out in the X-rays, how much more than a normal supernova is this? Like than a 1A or a 2? Or
Well, we don't really see X-ray emission from.
you just don't see any.
Yeah.
Yeah.
You see X-ray emission from
Maybe just the shock breakout.
supernovae that are also interacting with their medium.
Yeah.
So either in some type 1Cs, type 2Ns, where you have shocks, strong shocks that produce, very high plasma that emit in the X-rays.
Okay.
Or in things like gamma rays.
Okay. Okay.
So in the panel B there is a heat for the cow of an afterglow, right? Something which is flattening. So what about X-rays in that time interval, right? I don't see much.
So like from 10 to 100 days, are you
Or
looking
even
at?
later, after one, is there any follow-up channel or X-ray? Just to compare the story with the story of gamma rays versus where you have later on the external shock which collides with it.
It seems like there's a power law decay in the X-ray luminosity as time goes on. So the late time behavior, to my understanding of the phenomenology, does seem kind of like
But we don't get the point of that field, right?
that.
So because this is all quite early time. So the last point of the count panel is 100 years.
Yes, 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 yes.
That's optical, right?
That is X-ray and optical both.
R-band.
And so something that you see is that the X-ray is more, if you look at on the second page, something that you can see is that the X-ray is more variable than the optical infrared.
Yeah, but that is okay. That's really quite late time. It's you mean the dark blue, right? Dark blue. So this is still about 80 days.
I don't know what the latest time detection is. Maybe others do.
It wasn't cool. I don't know either. I think this is, okay, I think it's definitely consistent with synchrotron. I don't know if it's jetted emission. I don't think there there's been work on showing that has to be jetted, is what you mean by afterglow.
Right, anything which is later time which to
Yeah.
very shock, and
Yeah.
polite which are not circumstantial, but the static. So we're talking about 16, 17 centimeters.
So I mean, at 100 days, you're actually reaching about 10 to the 16 centimeters in this case. So I take your point that this is earlier time than you're talking about,
Yeah.
but I think there is some longer term follow-up.
Yes, sorry, this is why I wanted to ask that, not an extra, but they did a long-term, I can't remember now, in like blue optical, and there is a claim that you can still see the cow in the blue, and it's not an exact measurement, but their claim is that if it's not the cow, that part of the galaxy is incredibly blue in a way that's very suspicious. So it might be the case that it's still there, which is bizarre.
So is there actually a sudden drop here at 56, or is it an illusion?
I don't think so.
Okay.
I don't think
Kind of
so.
a cliff.
Yeah, I think if you sort of peer really closely at the blue points ahead of time, there is a lot of variability in those.
What about the black points?
The black points are pretty, I mean, they have a little bump there, but they're not. You don't buy it.
I see a cliff. I won't jump over this.
Okay, fair enough. You say no way. I don't know. Okay, that's the truth. All right, let's. Okay, Vinny.
So I was just wondering, so how would this plot, like the size of the photosphere, look like for normal progenitor of normal supernova?
Yeah, let's talk a tiny bit about that. So let's, what is the simplest version of a supernova? That's maybe if you have some total energy and you have some total mass of an ejecta. Then the characteristic velocity is going to be something like the square root of 2e over m, right? And Ito is raising the point that none of these have a single velocity. Then you would have just like a ring of expanding material. But instead, there's shocks and there's all this mass, and what happens is, and there's gradients of density, and what happens is you get a smaller amount of mass moving fast and a bigger amount of mass moving slowly. And what we see is some sort of photosphere where light is leaking out from some point within that expanding material. Okay, so you can imagine at first when that's as compact as the star, if it were to start expanding, the photosphere would just follow the edge of that material, and it would like expand with that gas because it's still mostly opaque. But then at some point you start seeing deeper in sort of mass element into that flow, and the characteristic sort of time scale for light to be able to leak out, you can estimate based on like when the optical depth becomes about 1. And you get that the time scale is on the order of kappa times the mass times b over c. So the things to notice here, and sometimes people call this the time scale of the supernova, and there's a 3 and a 4 pi from the volume that I left out. But here's the opacity. So if it's more opaque material, it takes longer to become transparent. If there's more mass, the density is higher, and tau, which is rho kappa r, is higher. And the bottom here, if it moves faster, it becomes transparent sooner. And so that's kind of the basic scaling. So when we talk, for example, if there's different composition of the material that makes it much more opaque, that can change this time scale. Okay. And the second question is, what is the luminosity of a supernova? And that's something like the internal energy at this time divided by the time. Okay? Does that make sense? Because when it reaches this point of transparency, the thought is then you start radiating away the thermal energy that's in that gas. And we can try to figure out what this is by splitting it up a little bit. So the first thing to point out is that as gas adiabatically expands, the internal energy is going to go down. And so for a radiation-dominated gas where the adiabatic index is something like 4/3, this means pressure is proportional to rho to the 4/3, then the internal energy is going to evolve as 1 over the radius.
Sorry, why is it adiabatic at this point? Shouldn't it be like ballistic?
Let's sort of imagine like you do something really dramatic, you blow up this material, you distribute its heat into both kinetic energy and thermal energy, and then it's just free expanding. And we're coming along and so maybe the supernova itself takes an hour, and then we're looking at it at 20 days. And so we're just looking at this cooling blast wave as it sort of freely expands. In reality, it isn't always adiabatic. And that's
No, just what's
Yeah.
why the transition?
So internal energy here is sort of like the thermal energy after the shock wave has propagated through the material, but not the kinetic energy, right? Like the kinetic term sort of has usually.
Yeah,
most
so
of
the internal energy is dropping and the kinetic energy is sort of staying the same,
it's
right?
kind of baked in, yeah.
Yeah. And okay, so then the internal energy at this time is going to be something like the initial energy times the okay, let me just explain what I have here. So it scales as 1 over the radius. So maybe you start with some initial heat content at some initial size, and by the time it's expanded to the point where the light can leak out, it's degraded by this factor of the radius, of the initial radius. Yes, please.
So if we integrate the energy observed for this object
Yeah,
back to the discovery people
Yeah.
based on the curve,
yeah.
so we probably can estimate the max of the project.
And what you get in this particular event is that it would be nowhere near bright enough. And so you need some extra, and this comes to Dan's point. Okay, so let's just finish this. So then we can estimate the energy as something like this quantity, which I just wrote down, the internal energy, over the characteristic time scale. And you could also write this as V times T.
So Morgan, I'm
Yes.
a little lost here.
Sorry.
Are you looking at the radiation energy or what is your internal energy?
The idea is that it's dominated by the radiation energy density.
And you're saying it goes like r to the minus 1?
I mean, we can work out where that comes from if that's helpful. So the density is proportional to r to the minus 3, right? And then the internal energy here is
It's the total, not the internal energy density, I guess.
exactly. So it's the energy density times the volume.
Volume, R cubed.
And so you have
Okay. I'll
Alright.
take your word for it.
Okay.
You're losing energy to doing work on the, right, like pressure times volume.
Exactly. Yeah.
No,
Yeah.
that part I understand.
Yeah.
Yeah,
Minus one is the
The
part
honest
I'm
answer,
getting in my head.
and so if you had 5/3, you get r to the minus 2.
Okay.
And the honest answer is every single time I do this, I have to redo the algebra. So it would take me a minute to do it on the board.
No, that's all
Sorry.
right. I'll take your
Um,
word. Yeah.
And I get confused about the units every single time. Okay, so what I want to point out is if you do this argument for a normal supernova, you would get a time scale that's, tens of days. That seems good. And you would get a luminosity which is about 10 to the 40 ergs per second. And that's actually not good, because a supernova is something like 10 to the 43 ergs per second. And so just the cooling off and emission of this expanding blast wave can't explain a normal supernova. What it means you need extra heat later, and later means at a time similar to when you're doing the emission, because you need to add internal energy at a time when it can efficiently radiate away. And there's two ways to do that. In normal supernovae, it's the decay of radioactive nickel-56, which has, and the reason why it's that species is because it has a half-life that's similar to the expansion time of the supernova. It can also be, for example, a non-adiabatic temperature evolution. So for example, if there's gas parcels slamming into each other at a radius that's similar to where the emission is happening, then you can convert that internal energy a lot more efficiently to radiation.
Maybe I'll add one more.
Yeah.
This whole scaling, which I'm working out in my head, the temperature does fall as 1 over R for the
Yeah.
radiation,
Yeah.
right? Whereas we know that the temperature you observe is not falling as 1 over R.
Yes.
So something is
Yes.
heating it up.
Yes.
So there has to be, this is not just like cosmology, you know. like the microwave background.
Your words. Oh, yes. Yes. No. Exactly. So, for example, in stellar merger transients, where you don't add any extra heat, you just see them get redder and redder and redder.
Exactly, yeah, right.
Neither a normal supernova nor especially this object doesn't do that. And so all of a sudden you know something else is going on.
There has to be some source of
Yeah.
heating going on, yeah. Okay.
Do you want to brainstorm on what could be going on for a couple minutes with the people next to you? And when there's 2 minutes left, I'll pass around one person's idea of what it could be.
I think it is important to remind though that because this is decaying so rapidly and it has a short time scale, that means the amount of ejected material is fairly small. So it becomes optically thin quickly.
Yes.
Radioactive decay cannot survive.
Yes. Okay. Sorry. Thank
At least
you.
you can rule that part out.
So that's the bottom plot on the second page. And what you see is that the vertical lines tell you the more ejecta mass you have, that's this scaling with mass to the 1/2, the longer a time of an event you will have. And so the fact that you're at 1 day, which is sort of at the very leftmost point of this plot, tells you that the characteristic amount of mass is small. And then the sort of curved curves, for lack of a better word, are the combination of time scale and brightness that you get if a different fraction of the total mass is radioactive nickel-56. And basically the fast blue optical transients live at about 10 to the 44 in luminosity and 1 day, so on the y-axis at 10 to the 44, and they're just way out of the region that you can ever do with nickel. So it's not. Is that a good summary of that point that you're making, Ito? Okay.
Or I need 100 solar masses of nickel?
Well, but that gives you too much opacity,
Oh, yeah.
right?
Yeah, so if
even
we
with
would do it,
100% nickel composition, you wouldn't have enough luminosity from the radioactive input relative to the opacity, the limit that you have from the short duration.
yeah. Yeah, but
So do I understand correctly from this plot that this scaling that fits nicely, right? So it's just luminosity goes as 1 over t squared.
But this is not thermal.
Um,
The plot you're looking at, this one,
Yeah.
this is the non-thermal
Ah.
emission now.
Which one, the
Okay,
T to
then.
the minus 2? I think T to the minus 2 is the kind of inferred total energy input into the system.
Okay, but
So it's something that's more like a power law rather than radioactive decay, which is exponential.
right, but how does like extra heating fit? So is it like some extra heating that must not change this power law behavior, or?
Yeah, so if there is extra heating from radioactive decay, you would see it following an exponential. And in fact, you can see like a break in some of these really long-term light curves, like where it's different species half-lives set the decay, like from nickel to cobalt. But yes, I guess if it were pure cooling emission, you would have the same power law timescale, but different color evolution.
So, is there any obligation to say the fraction of the non-thermal part and thermal part evolve with the time?
It seems like the non-thermal component becomes more important as a function. Okay. So it sounds like something that we're all arriving at is you need extra energy, and that we had a hint of that because Raffaella calls the bolometric luminosity L engine. And so the idea is in there is that there is something driving this power, and there's a power source at the center of this object, and we need and we need a way to turn that energy into emission. And maybe, I don't know, Dan, do you want to like reiterate what you were saying about like collisions driving emission?
Well, yeah, I mean,
I can
I
try.
was just saying, if you're outside the photosphere, then it's really just anytime you have shells hitting each other, you'll get photon production and possibly a boosted frame, although not this one's not very boosted. But
Yeah.
So then you would just get direct energy, direct luminosity out. You don't have to worry about the radiation transfer.
Okay. And if you're doing that deeper, you're saying.
Well, if you're inside the photosphere, then you have to get the photons out.
Yeah. Yeah. Okay. Okay. So, and I think the other clues are we have material moving at a bunch of different velocities, right? And that plays into the fact that there are these collisions. Yeah, go ahead.
Yeah, is there a common story being told in the prominent spectral features that form once the thing's cooling off? Among the events like that?
I don't know, other than that there's sort of a broad range of species there.
Yeah.
It's not that they're completely hydrogen depleted or helium depleted. That sort of thing.
But the velocities at late time are much lower, right? So it's
Sure.
possible that you're seeing some CSF material rather than just velocity.
Yeah. The composition of the CSM being hydrogen rich, something.
So the model that's kind of emerged is that you have an engine and you have a CSM, and there's some outflows that are sort of 0.1 C, and there's other outflow that's like 0.01 C. Maybe that depends on angle. There's polarization in some of these sources. And the total mass out here is of order 1 to maybe 10 solar masses. You can estimate that based on the sort of luminosities of those non-thermal components. The mass in here is much smaller, maybe a fraction of a solar mass in that fastest material.
If the angle is a problem, so if you have a large sample, you probably might have much output.
I think the idea is that this material is mass rich enough that you're not getting like a jet tunneling out of this material and this really strong viewing angle dependence. You're like getting an outflow that's almost relativistic, that is sort of impinging energy on a broad range of angles, versus say if something was going 0.99 the speed of light, it would be collimated and sort of directed flow. So let me show you, I'm going to pass out sort of both a summary of the properties from Rafaela on one side and then one model from Brian Metzger for these sorts of things on the other side. And Rafaela also has a table of the possibilities. And I think that's as good a place to leave it as any. So the model that's out there, I just wanted to point out, it has a lot of steps, right? It's you start with some stars, you throw out some hydrogen, and then later maybe you have a merger of two stars and there's a black hole in the middle of another one, and that accretion onto a black hole is the central engine, and it has to be exactly the right number of years after the hydrogen is ejected.
It's ugly.
And it's really, and it's like maybe you can do anything you want with a binary star, but it feels finely tuned. But I think the idea that, so if we flip it over and look at the table on the bottom of the other page, it has some notes on these velocity scalings that I tried to show you on the board from Dan Kaysen, and then it has a table from Rafaela Margutti, and what you see there is that there's a number of possible sources which may or may not explain the presence of these different spectral features, the rise time, the decay time, the CSM. And I think that's really the state of what's known. Yeah, please.
Just a context of this wonderful cartoon from Brian. That part of this, right, you said it's fine-tuned. I think part of this is coming from the fact that we're now seeing this weird zoo of stripped envelope transients. So I have lost my hydrogen helium envelopes. I'm not saying the cows necessarily fall into that, but increasingly Brian and friends are trying to find a unified picture of that full zoo of possibilities on fully stripped, ultra stripped. I make like neutron star binaries.
Yeah.
To, I actually seem to have lost this very recently, and so my CSM is really enriched with material. And so that's why I think this binary setup exists, is because it fits into this like picture that he would like to put many ideas within.
I think it's interesting, and I mean, I think basically it's not fine-tuned in the sense that if all that hydrogen were closer to the original source and moving more slowly, you might see something like what we call a 2N supernova, which has narrow lines from the slow-moving hydrogen. And if it's further away, we might see something like one of these sort of strict supernova where you don't see CSM interaction until very late. And so it's at least plausible, but it's not the only explanation. I think that's all I wanted to say.
Do we have any constraint on the engine, or is it you just like could be magnetar, could be an accreting black hole?
There is some evidence of like quasi-periodic oscillations, that sort of thing. So it's the black hole mass can't be too high if it's a black hole. That's my understanding of this level of constraint. So I think probably we should stop there. We're at the hour. I've been so grateful for all your questions. It's been fun to read and learn about this. I hope this was productive for you all. If you're interested in this, there's a link to, I made a like ADS bibliography of the papers I was reading as I put this together. So there's a link to that, and it's even a QR code, which is extremely high tech of me. Yeah, so I hope this is interesting or helpful to you all. Thanks.